Today we're going to do section 5.2, page 502, where we're going to take the double integral over some kind of a weird region that isn't a nice clean rectangle anymore. Now to look at that, the region, as your book puts it, they have a type 1 region and type 2 region. And basically what it is, they're the same thing. Basically what it is that there's a change only in one direction. This is, for example, look at this shape. The xy goes from, the x coordinate goes nicely from A to B, right? But the y coordinate will vary from some function to the next function. And similarly to the other pictures, that is what called the type 1 region. And what you do is then you integrate one of them from, in this case, from A to B, but that's x, the dx, whereas the dy you integrate from g1 to g2, the function. So what you're changing is the the limits of the integration. And similarly, if your thing is where x and y, where y coordinate goes from a constant from C to D, but the x coordinate is what's changing. See, x coordinate might go from a function to another function. The same principle applies. So with that, please do example 5.11, where you look at the different regions a little bit as part of your homework. Now and then let's turn over the page. Let's go to page 504, where we look at Fubini's theorem strong form. So that repeats what I just said, which is that the integration is of these two regions that we talked about, whether it is where x has constants from A to B, whereas y has variables, okay? And you will substitute the variables in there, and then you perform the integration like you always do. Now, and then similarly, if y is the one that has an integration involved, then you will substitute it. So then, whatever this is, whatever is having the variable, right? And so y is going from C to D, whereas x is going from the two functions. So you plug it in there and you perform the integration just like it says. Now you might wonder, if there are integrals where the limits also have a variable, how does the integration work? Now remember that when you integrate with respect to y, like this example here, this is example 5.12, please do that as part of your homework. Like when you integrate this, like first when you integrate is you do y first, right? Because y is on the inside. You go, y goes from x to half of x to 1, and there you have x squared and stuff. And why there's so many x's? It doesn't matter. Remember, this is similar to partial derivatives in that x, because you're integrating with respect to y, the x's are just constants in this case. So you just plug it in there like some number and then keep moving. And then your answer will come right out. So please do example 5.12 as part of your homework. And actually that's probably what we did, or you've done already in the previous. Maybe not. Well, whatever. That's what we're going to do now, okay? That when you're integrating with respect to y, then x is the constant, whether it is inside the function or at the top, upper, or bottom limits. Doesn't make any difference. You plug it in and do integration like you did in Calculus 1. And then, okay, now the same as example 5.13 on the next page. Please do that as part of your homework, where you're integrating over a type 2 region. Doesn't matter what type it is, it works the same way. You just have to be careful and figure out which way am I moving. Am I doing dy or dx? Okay, and then what is being changed? Okay, so you keep all your upper and lower limits correctly. And then let's flip to the next page. And then we are looking at theorem 5.5 on page 507, where we now have to concern ourselves, what if you have two separate regions? Well, as long as you have two separate regions, then you just integrate from each region, of course. So then, so that is all it takes, really. So basically you have two problems instead of one, which sounds like a lot of work, and it probably is, but please do that as part of your homework. And with example 5.14, Next, let's look at changing the order of integration. That changes nothing, okay? Sometimes you might have an option of integrating x first or y first. Makes no difference. So please do example 5.15. What you do is you see which one looks easier and pick that one. Sometimes it's obvious, sometimes it's hard both directions, so pick one. So that's example 5.15. Please do that as part of your homework. And 5.16, same thing. Now let's keep moving. Next, we're going to calculate volumes. Now we're going to calculate volumes the same as we did before, which is you have a surface and you're going to integrate, but this time instead of integrating over a rectangle like we did, now you're going to integrate over some other shape with the same trick that we just mentioned, okay? X might go from a number to another number, whereas y will go from a function to another function. But otherwise, it works the same way. And that's so that's example 5.17. Please do that as part of your homework. Next, for example 5.18, there is a definition that the area of a region can be defined as the double integral integrating by 1. If you integrate something over a region by 1, that will automatically give you the area of that region. So to find the area of a region, then you can integrate over the region by 1, I guess. Or just do it the calculus one way, which end up being the same thing as far as I can tell. Anyway, so please do example 5.18 on page 512 as part of your homework. And next, we have the average. The average, as defined as always, is the integral divided by the area. Okay, so the average of a function is you integrate the function over the area and divide by the area itself, and that is defined as the average. Yeah. Anyway, so knowing that, then you go ahead and do it. That is example 5.19. Please do that as part of your homework. And next, we are looking at something called improper integrals. The improper integral is similar to the improper integral in the calculus 1 in one dimension, where it's called improper because something odd might be happening. For example, there might be a division by 0 happening, or your area that might be going to infinity. That is, your area isn't bounded. Now, in that case, it can sometimes still work with certain conditions. Please look at page 515. Okay, we're looking at Fubini's theorem for improper integrals. By this theorem, it says that if D is a bounded rectangle or simple region in the plane, and f is some non-negative function on D, that's important, okay? In this particular theorem, f has to be non-negative. With finite many discontinuities, then what we've been doing so far works in this case. That is, you can integrate it like we've been doing, okay? X, for example, x might integrate from a to b, and then y might get integrated from y equal to gx, that's the one curve, and y equal to hx, the other curve. And then you crank this thing out. This has more conditions. And what does finite many discontinuities mean? It means that it can't go crazy and has infinite number of discontinuities. And you might think, why would a surface has an infinite number of discontinuities? It's possible, if you have a bunch of holes and the holes are in a sequence that approaches something, an infinite sequence. Okay, it has an infinite sequence of holes, for example. That's just one of many examples why it might have infinite many discontinuities that will give you a headache. But we're not going to deal with that in this class. We'll just have something that's nice and smooth, and maybe have one discontinuity, and then, or maybe the area is looking pretty decent or something. In this case, it's just a bounded one. Anyway, yeah, so basically you're going to do the same thing you've been doing this whole time. So please do example 5.20 as part of your homework. And next, what's that? Okay, that next one, the last theorem, is on the following page, 516. We are looking at theorem 5.7, where we're integrating over an unbounded region. okay? Now, in an unbounded region, again, with if various rules, well, doesn't matter. The point is it works, okay? We'll just take the limit and like we did before in Calculus 1, and then everything will work out. If, well, in this case, it's just an unbounded rectangle. That's all we care. We don't have some unbounded weird shape, okay? It's just a rectangle. Yeah. Well, why would there be an unbounded rectangle? That just means, for example, the first quadrant, okay, x bigger than 0, y bigger than 0, that is a rectangle that, you know, goes on forever. You can call it a rectangle. You can't see two sides of it, so we'll just call it that. But anyway, when that happens, things do work out according to this theorem. Now that you know that, then you go ahead and do that the same way as you do the improper integrals in the past. You integrate and you push the limit to 0 and see if something good comes out of it. And that's example 5.21. Please do it as part of your homework. And next, now we're on page 517. The page 517, your book is starting to talk about some probability concepts that if you were to read it, you might understand only vaguely what it's talking about. That's not important, okay? You just you just read it, and if you don't understand it, it's of no consequence. Just look in the example and make it to the point where it says, where it comes to the double integral, because we're doing double integrals, so double integral is all we care about. Then go ahead and do the double integral, and then you're good. Okay, that it would be. So please do example, what was this again? 5.22 as part of your homework. And then example 5.23, same thing. Okay, there is some probability concepts being preached to you. We're not doing probability right now, so we don't really care. Just let's get to the double integral and then crank it out, and then you're good. So that is example 5.23. Please do that as part of your homework. And with that, we have come to the end of this section. Now I know that this section seems to have a huge number of examples as part of your homework, but please do them anyway, because they do cover a broad ground, and I feel that they will give you a solid grasp of understanding of the material. The integration itself is identical to what you did in Calculus 1. So that shouldn't be much of a problem, although it will be very time-consuming probably. The homework, for the most part, seems to be easier than the examples, so that is a benefit. For homework, on page 521, please do problems 77, 81, 85, 89, 91, 95, 99, 101, 105, 106, 107, 113, and 21. And when you are done, come back, and I want to talk about some of the homework. Now that you're done with the homework, let's talk about it. I want to talk about problem 91, which is actually a neat little homework, but there's a small point that I want to mention. That is, you're integrating, you're calculating the area, so you're integrating 1, right, from the respective limits. And then when you do that, then being that you're only integrating 1, you are just end up integrating 4. So it's 4 times 2 pi over 3, which is 8 pi over 3. However, what actually is happening is, so the problem seems quite straightforward, right? Short and sweet. I just want to mention that if you imagine this area as a bunch of skinny sticks standing up, okay, along this curve thing, all right? You have a bunch of skinny sticks, and what happens is, imagine that you just, instead of standing on a curve, you let them all drop down to flat ground. Then in that case, that is just a rectangle that's 4 by 2 pi over 3. And that's why this integration works. Not that it matters that much, but I just want to mention it. So next, let's look at problem 106, where we have a theoretical problem, okay? Not many numbers in it. So let's look at this problem where we have the area, okay, which goes from A to B, and then from 0 to the function g. And then there's the function z, which is of x and y, equal to g prime of x. It doesn't have y in it, but that means nothing to us, okay? We'll do the math like we always do. So we plug it into the formula, which is this, and then we integrate And then when you're integrating, remember, when you integrate with respect to y, the g of x is just a constant. So then you end up being here. See, you get this, which then when you integrate this thing, you have gx and g prime of x, which is just gx squared over 2. Where, because when you take the derivative of gx squared over 2, you apply the chain rule, that's exactly this thing. Okay, and then you evaluate it at x equal to a to x equal to b, and then you get what you're looking for, exactly. Okay, and that's problem 106, I believe. See, right there, short and sweet. It's nice to see a double integral problem doesn't wear you out. And so next, let's look at problem 113. It is we have a bunch of pile of surfaces. Okay, here's the first surface, second surface, and then what are the other surfaces? Oh yeah, I think x equal to 0 and y equal to 0 or something like that, right? So after all these surfaces, and you're supposed to calculate the difference, the area of the solid. So the best thing to do to do this kind of problem is let's use Desmos 3D, graph this thing, and see what it looks like. So that's what I did. Now I graphed it, and if you graphed it, you probably have something that looks similar to this. Anyway, so I have a kind of a shadow there for some reason. Maybe I turn it. Okay, that seems a little better. All right. So as you can see, this looks like a complete mess, right? I mean, what is that? What are we looking at? So to fix that problem, you have to adjust this thing and see exactly what we're looking at. And then so I adjusted it, and then things were looking much better. Okay, after some adjustment, that is, I changed the range, which, as you can see over here, wait for the camera to zoom in, where first I checked the translucent surfaces on top, and then I unchecked the XY plane on the bottom to get rid of it. But I guess that wouldn't have hurt anything. And then I have the x-axis. You notice the values I type in, that makes things look so much better. So as a result, this thing now looks like this. I'll fix that reflection problem later. Anyway, so now our surface looks like that. Okay, that is much clearer. It's two tetrahedrons on top of each other, and our job is to figure out what is that volume in between these two things. You know, the volume right in here, right? There's the bottom one, the top one. So we need to do the top one subtracted by the bottom one, and that's what we're going after. So now that we have seen what the thing is supposed to look like, then everything looks much easier. First, what is the bottom area? The bottom area, as you can see, is where z equal to 0. If you set z equal to 0, both equations returns x plus y equal to 1 right here, or y equal to 1 minus x. Now, which means they intersect along the same line, which is what this graph shows as well. See, they intersect along the line y equal to 1 minus x, or x plus y equal to 1. And so it doesn't just look that way, it actually is true. So that makes things a bit better, okay? Well, I don't know if it does, but we're gonna just go ahead and do this. And so we're gonna do the double integration. And the first, and we're integrating for x equal from 0 to 1, y from 0 to 1 minus x. So the surface S will be S1 minus S2. But when you look at it more carefully, you notice certain qualities about S1 and S2. S1 happens to be twice of S2, right? Because if you factor the 2 out, then that's exactly the same as S2. Anyway, but I'm just going to subtract this, and I get this thing. And then after some integration, I got the answer 1 over 6, which is correct. And notice that this thing also happened to be exactly the same as S2. Okay, so here's S2 also equal to 1 over 6. And then the original S, what is that? Oh, S1, the original S1 is equal to 2S2. It just happened to be that way. So then it equals to 1/3. So that is the answer to our problem. And then finally, I want to talk about problem 121. Now, 121 is such a cute problem, right? remind us of problems that we learned back in, when did we do circles and triangles? Maybe, I don't know, 5th grade or something? Maybe geometry in high school, probably 5th grade. Maybe 6th grade. Well, whatever it is, we're going to calculate the area of those two lunes. A lune is a moon, okay? Is a lune, does lune means moon in English? I don't remember, but it means moon in some other language. Anyway, so here we're going to do this problem, and the way we're going to do it is the same way we did back in 5th grade or whenever it is that we did this, okay? So we are going to calculate the area. First, we notice the Pythagoras theorem. My triangle has dimensions 2a, 2b, and 2c. All right, as indicated in the picture. And the two lunes are called L1 and L2. First, let's look at 2a, 2b, and 2c has the Pythagoras theorem, which satisfies that, right? Which end up being a squared plus b squared equal to c squared. Again, the Pythagoras theorem. Now, the area of the triangle, if you use base times height over 2, is 2ab. The area of the semicircle, what semicircle are we talking about? Oh, it's A1 and A2. Now, when I say semicircle, I mean A1 is L1 plus H1. H1 stand for the whole over there. And then A2 is L2 plus H2. Okay, it's the moon plus the whole. That together makes the semicircle. So A1 is pi r squared over 2 because it's a semicircle, so it's A2. And then the area of the circumcircle, that is that thing. You can see the circle over there. That's whose radius is c. Okay, the circumcircle is the semicircle that that touches all 3 points of the triangle. Okay, so that is pi c squared over 2, and then the area of the holes. How big are the holes? And we don't care what they are by themselves. We only care about what their sum is. So you take the semicircle subtracted by the triangle, and that gives you the sum of the holes. And then the area of the two lunes. The area of the two lunes, L1 plus L2, will be the area of the two semicircles, A1 and A2, subtracted by the area of the holes. And so when you plug everything in, remembering that a squared plus b squared equal to c squared, you quickly came up with 2ab, which just happened to be the area of the triangle. Now that is the solution also. Now the book, I don't know what the book wants with the double integration, and I don't know how to do that for this problem. And even if I did, I'm not doing it. Okay, this is good enough for me and everybody, right? It's super cute to see such a problem. It reminds us of the good old days when in 5th grade when we were doing this kind of stuff, right? It's such good times. So that marks the end of this section.